Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Average Value of a Function on an Interval, and as always, please be an active learner as you watch this video. By way of introduction, here are a couple of forward-looking examples of the concept that we're talking about. So in this first example, the temperature is a three-dimensional function. It is a t of x, y, and z. That means that the temperature changes as you're in the x-axis, y-axis, and the z-axis. And that temperature we're interested in that along a wire helix C, which is a three-dimensional curve given by the vector valued function r of t is equal to pointy bracket sine of 2t, and the cosine of t. And this is the distribution of the temperatures based on their x, y, and z. And so the questions so here is a picture of that three-dimensional curve. And then, so what are the temperatures at various values of t? And the temperature is always changing, so you might be interested in what's the average value along this helix, and so you're interested in computing the average temperature of the wire, and you're going to be using concepts that we're going to discuss today. Now, this example does involve three dimensions and line integrals, but the averaging concept is the same. The three dimensions and line integrals are COD Calculus 3 fare, but the concept of parametric equations, which is the whole idea of bringing this t in, will be discussed in COD Calculus 2. So this is a forward-looking example, but it is an example of using the concept that we're talking about here. A second example comes from the ideal gas law. You might study this in thermodynamics. Actually, you could, I suppose, study this in thermodynamics as well. And this is an issue involving the Maxwell-Boltzmann distribution of speeds of molecules. And so the distribution for speeds of molecules, all molecules are not moving at the same speed. There's a bell-shaped curve that describes this. And you have a most probable velocity, you have a root mean square velocity, but also you might be interested in the average velocity. And this distribution function can be shown to be f of v is equal to 4 over square root of pi. That's the mass of all the molecules, that's the temperature, that's a constant depending on the ideal gas. This is v squared e to the mv squared all over that 2k 0 of the gas times t. Now, this example involves integration by parts and improper integrals, both of which we cover in Calculus 2. And in fact, I have asked this question on the final exam testing both integration by parts and improper integrals. So this is a second example of being interested in the average value of some functions. In this case, it's the average value of velocity. In this case, it's the average value of a temperature. With that as a motivation, then, let's define the average value of a function f over an interval ab. Now, this is a continuous function, f of x over ab, so it can be constantly changing, is given by the average value is equal to 1 over b minus a. That's the 1 over the length of the interval, and this is the definite integral from a to b of f of x dx. Now, this really is not a definition, this is a theorem. So let's talk about why this is true. And we go back to some basic principles. Here's what we're going to do. We're going to take the interval a, b, and we're going to divide it into n pieces. And so we're going to say that each of the subintervals then is delta x is b minus a over n. They're all the same length. Now, if I were to solve this for n, I get that n is b minus a over delta x. Now we approach this from creating a discrete situation and then taking limits. So for each of those intervals, delta x, we choose points x1 star, x2 star, xn star, and we take the average of those. So you see we're taking the average value of f of x1 star plus f of x2 star dot dot dot, thank goodness for dot dot dot, down to f of xn star, and we divide it by n. So now we're going to substitute this expression for n. So we stick it in there and we do the arithmetic, and we see that the delta x comes to the numerator. Make sure you follow these calculations. So that's the same thing as b minus a times this sum, which is this, and we're recognizing this then, at least this summation part is that is a Riemann sum. And so what we're able to do then is we're going to take the limit of that. That's the average using this, but if I take the limit as n goes to infinity, what you see is that the b minus a is a constant, so I can jerk it through the limit. And this becomes the definite integral, so whenever we complete this, we have that the average value of a continuous function, continuously varying over an interval ab, is 1 over b minus a times the definite integral of, from a to b, of f of x dx. So here's an example, and there are two problems here for you to do. So the directions are to determine the average value of each of the following functions on the given interval. So this one has the interval going from -1 to 5/2, and the function is f of t is t squared minus 5t plus 6 times cosine of pi t. And the second problem has the same directions but a different function. This is capital R of z is equal to the sine of 2z. This is e to the 1 minus cosine of 2z. And here we're talking about on the interval from minus pi to pi. Now, I do expect you to pause this video and give this a go. It allows you to review the integration things, and even if you don't get the right answer, you're well prepared to look at the solution. So I do strongly encourage you to pause this video, work the problem, and after you find your solution, come back and hit play and look at it. So you know what to do. Let's see how you did. Okay, so there's not much to do on this. This is 1 over b minus a, and I'm integrating from -1 to 5/2. This t squared minus 5t plus 6 times cosine pi t dt. So I enter it. Now this is going to be 1 over 7/2, which is 2 over 7. But then I perform the integral. So I add 1 to the exponent, divide by the new exponent there. And here I take note of the fact I have to do a u substitution, that the integral of the cosine is the sine, but I pick up this factor of 6 over pi in the denominator. And then I do the fundamental theorem of calculus. I substitute these values in and subtract them. And this is the actual exact answer, which I will be looking for. And so this is 12 over 7 pi minus 13 over 6. Now, if you plug this into a calculator, this really should say approximately equal to this number, because this is an irrational number. So this is the exact answer. That's what I'm going to be looking for, and I will be expecting you to actually perform these calculations. So this is good practice for you. In the second function, what we have, the graph of it looks like this. You notice that there's some positives and some negatives from the integral. And if you look at this, you say, wow, they almost look like they're the same kind of numbers. And in fact, we'll see that that happens. But we do, in this case, have to do a substitution. So here is the function as we start out with. It's 1 over b minus a. Notice a minus times a minus ends up being a plus. We're getting from minus pi to pi of sine 2t e to the 1 minus cosine of 2t dz. Now, to evaluate this integral, you have to use a u substitution. This is the u substitution you use. And when you complete that, you should end up with a 0, which means the positive and negative areas cancel out, and that means the average is 0. Now, you could think about this as being a corollary of the original function, but there's a mean value theorem that we have not only for derivatives, which you studied in Calculus 1, but this is the mean value theorem for integrals, and you're studying this in Calculus 2 at the College of DuPage. So if f of x is a continuous function on a b, that means it is integrable. Then there is a number c such that the definite integral from a to b of f of x dx is equal to f evaluated at that c times b minus a. And when you think about this, what this is, and you can think about why this is a mean value theorem, that this again is an existence proof. It doesn't tell you what C is, but there are problems where you will have to find C, and we'll do an example of that. But this is an existence proof, okay? So we start out by defining capital F of x equal the integral from a to x of f of t dt. Now the fundamental theorem of calculus, and I don't know if this is part 1 or part 2, but that tells us that this is a continuous function of x. And in fact, more than that, this is a differentiable function of x. So capital F of x is continuous on AB from calculus 1, is differentiable on the closed interval, and capital F prime derivative of that at x is equal to f of x. There's actually a lot of calculus 1 involved in this part. And then we also use the mean value theorem again from calculus 1, which tells us that there exists a C. We don't know what it is, but C is between A and B such that capital F of B minus capital F of A is equal to capital F prime of C times B minus A. But we know that F prime, capital F prime at C is f of x, and that means that f of B is equal to the integral from a to b f of t dt. And that's the same thing as the integral from a to b f of x dx, because that really is a dummy variable. And we also know that f of a is equal to 0 because the integral from a to a of f of t dt is equal to 0. There's no area under a single point. And so whenever we solve this, then what we end up with is f of b, which was this integral, minus f of a, which was 0, is equal to capital F prime at c, which is really lowercase f of c, times b minus a. And we have proven this assertion. Note that one way to think of this theorem is the following. If we rewrite it this way, that means that there is a value of c between a and b such the average value of the function over ab is equal to f of c. And here's a picture, so that says there is a c such that this integral, that if you make a rectangle whose length is b minus a and whose height is f of c, there is a c such that this area of the rectangle is the same as the area under the curve. And in this particular example, you can see that this positive is interacting with that negative, and they're equal to one another, and that's why you can replace this down here and do it. But we've already proven that theorem. So let's look at an example using this theorem. Again, you're supposed to be doing this. Determine the value C. Now the theorem doesn't tell you what the value is. You have to find it. So determine the value C that satisfies the mean value theorem for integrals for the function f of x is equal to x squared plus 3x plus 2 on the interval from 1 to 4. Now you know what to do. Let's see how you did. Okay, well, you know that the function is a polynomial, so it's continuous. It's also integrable and differentiable. That means we can use the mean value theorem. So there is a c such that the integral from 1 to 4 is equal to, and we evaluate the function at c. So we plug c in here, and we get that times 3. Now we evaluate this integral, and you should do this, adding 1 to the exponent in each case and doing the calculation. You get 99 over 2, and on this side you get 3, 4 minus 1 times c squared plus 3c plus 2. You distribute, and then you end up with a quadratic that you have to solve. Now, we solve this using the quadratic formula because this doesn't factor. Everything doesn't factor, and I have asked questions like this on assessments before. So we find using the quadratic formula, and you should go through these steps, that c is equal to minus 3 plus the square root of 67 over 2, and c could also be minus 3 minus the square root of 67 over 2. But we're looking for the one that is in the interval from 1 to 4, and so only the top one is there. And again, realize that I will be asking you for exact values, which involve the square root of 67. Now this one is not in the interval, so that's not the one we're looking for, and so this is the answer. It would be possible for there to be more than one. What the theorem guarantees is there is at least one. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. God bless you all.